Formal Lab 2 Playdoh Circuits by Group 4A, Cameron Bennett, Paige Bryant, and Tiara Mosley. First of all, our introduction and our main ideas. The purpose of this lab was to build a circuit with LED light in parallel to an electric motor, including Playdoh as a resistor. Our parallel circuit is two or more paths of electricity to flow in which two branches are parallel to each other. Resistivity is what we're aiming for. We're trying to find the resistivity of our Playdoh, and it's the measure of the power of a material to resist the flow of electric current. Looking at a couple of our math problems, we have R equals PL over A, in which P equals resistivity, L is the length of the resistor, in this case our Playdoh, and A is our cross-sectional area of our Playdoh. To find the cross-sectional area, we first had to find the surface area of our Playdoh using S equals 2 pi r squared plus 2 pi rh. This equation was necessary in determining the surface area of our resistor. We then modeled our circuit using the FET-SIM and made predictions based off of the data from the simulator. As you can see, our model consists of 3 batteries. Our first loop has a 1.5 ohm resistor in series with a fan motor, and then there's also an additional parallel loop that has our Playdoh resistor and an additional light bulb. Our experimental design was to determine the resistance of Playdoh by recording the voltage drop across the resistor and the current as we modify the length of the cylinder. We created a parallel circuit in which the Playdoh resistor can run an LED light and a fan at the same time. We use this using alligator clamps, an LED light, a pre-molded cylindrical Playdoh-shaped resistor, Playdoh resistor, a 1.5 ohm resistor, and 3 1.5 volt batteries. The voltage and current flowing through the circuit can be measured using a voltmeter, and the motor and 1.5 volt resistor were in series, and the parallel to the light and Playdoh resistor that were also in a series. As you can see, our circuit, we have our multiple batteries, our 1.5 ohm resistor in the middle. It's quite small, so you can't see it very well, our fan motor, our Playdoh resistor, and our LED bulb. Our experimental measurements are as follows. The LED bulb we measured at 2.86 volts and 3.62 amps for the current. Our Playdoh resistor was at 2.02 volts. Our fan and motor setup was 0.20 volts and 0.29 amps. Our resistor, the regular 1.5 ohm resistor, was at 4.62 volts, and our batteries measured across them was 4.93 volts. And then some statistics for our Playdoh resistor. The length was 4.4 centimeters, the diameter was 2.5 centimeters, the calculated surface area was 4.91 centimeters squared, and the P as determined in the pre-lab was 0.0085. Our results are as follows. Using the variables outlined previously, we found our R for this resistor to be 0.076. Sources of error in this lab included the moisture level of the lab air environment. Corrosion of the wire was especially concerning because Playdoh corrodes the wires that we were using quite rapidly, so we had to change the wires out every trial. In this scenario, corrosion of the wire decreases resistance and also increases the current. And additionally, area. We started with a rather large Playdoh resistor, and we found that a larger area increases resistance and decreases current. So it took quite a bit of troubleshooting to be able to get our light bulb to illuminate. As I mentioned, our troubleshooting, we had to reduce the size of our Playdoh resistor. We played around with moving the location of our 1.5 ohm resistor to see if we changed it in the order of the series or moved it around in different places, how it would work. Going off of that, we also changed the orders in the series. So would it be better to have the fan first, or would it be better to have the resistor first, and vice versa? And then we also changed our junction setups. They got pretty complicated, so we played around with them quite a bit. Thank you very much.